Hello again, everybody. It's Johnny back here on our series about introducing mathematics for machine learning and artificial intelligence. One of the core algorithms in machine learning is what's called the gradient descent. You may have heard about it. I want to get into that at some stage, but I thought we'd just have a very quick reminder about what do we mean by gradient. Sort of aiming this series of videos at people who have no real mathematical background. I'm trying to make it very simple. So for those in the know, forgive me, I'm going to go back to something incredibly basic, which is to talk about how we measure the slope or the gradient of a line in mathematics. Now, this, when I started thinking about it, actually reminded me of something that happened a little while back in the United Kingdom. When I was a kid, we used to go on camping holidays. We'd be camping next to the lake in the mountainous district of England, and we'd see signs like this, and we would read it as 1 in 4. Dad, there's a 1 in 4. It's put on the brakes. Nowadays, all the 1 in 4 type road signs have been taken out, and you can see this is actually the same place, and been replaced with percentages. It's 25%. Both are perfectly valid ways of measuring slope. It did make me laugh, though, that the Guardian readers, in their infinite wisdom, decided when this change was made to hit the the social media comments. When and why did they go from a perfectly understandable to a quite meaningless? It's not meaningless unless you're woefully unnumerate. Then gradients are more readily understood. There's nothing more woefully illiterate than to describe me as woefully unnumerate. And anyway, you get the point. So, and it just went on and on and on. I really do not understand people who, insist on doing this. I like that one. Why don't we just say it's gentle, it's steep, or bloody hell? So yeah, you get the point. Lots and lots of trolling and things was going on at the time of this change. So without further ado, what I want to do is, of course, go into my old friend, which is Desmos. And here we are. I will bring up a diagram. And there we go. Desmos diagram for you that is very simple. How we define slope. I've got a sloping line here. And it doesn't really matter where I'm looking on the line. I can be looking anywhere on the line, it has the same slope. But what I've done is I've got a variable here called delta. And delta, I take a step delta in front of my point and delta behind, and I calculate the two heights. It's terribly simple. I can just kind of go in here and let me see if I can pick this up, if I can move this here. This is basically just like our sort of 1 in 4. Modern day way of teaching this, they call it the run and the rise. And what you do is you run from this point. We run 2 delta in length, that's our 4, but we go up or down 1, that's our rise. If it was the other way, -1, we'd have a negative slope. So this could be, we rise 1 in a run of 4. It's a 1 in 4. Essentially, that would be a calculation then of 25%. And that's it. That's basically how we calculate a slope. When we're interested in expressing a slope in mathematics, it's terribly simple. It's just something that we, the run and the rise, the 1 in the 4, the 25%, it's all the same to me. Now, eagle-eyed people might wonder why I've got pi down here. So the first thing is that's because I'm going to actually start looking at some more funky curves. But before we do that, was my function. It is 0.25x. It has a slope of 0.25. Now, I've actually put down here the calculation. This is our run and rise type calculation. So I take the height at, which is whatever the function gives us for my point that I'm interested, but I'm moving a delta to one side. I subtract off this height, that gives me my rise, and I divide it by my run, which is 2 times the delta. Do the calculation and it comes to 0.25. It really doesn't matter where I am on this line because it's all got the same slope. The 0.25 never changes, and I can take a big delta and I can take a small delta, and I always get the same. If I get a delta of 0, I'm dividing by 0, I've got no run. It's not impossible to measure a slope when we don't move, if you like. We're just looking at a fixed point. And this becomes highly relevant when we start looking at lines that are not straight. So I'll get into that. I'm going to change my function, and let me put in something that I know is wiggly. I'm going to put in a sine function. And it becomes a lot harder for us to say, well, what is the slope at any particular point? So here, once again, I can sort of move into sort of different points. There's my point. What is the slope there? Well, the problem is it actually, let me bring back my function, my calculation. If I take this step, my run, I move back a step and I move forward a step, I can calculate my run is still 2D. There it is. And I've got a rise, and it's the sine calculated at this point, which is the point I'm interested in, plus delta. The point I'm interested in minus delta, calculate the sine. We can work out our rise. We know our run is 2D. But this is not actually the slope at this point. It's an approximation. It's the slope from this point to this point. And that's not really the exact answer that I want. The whole crux of differential calculus, calculating slopes, is if I can make this smaller, my estimate becomes better, because, I'll zoom in, my straight line becomes a much better approximation of my curve line. You can just see a little bit of blue in there. Oh, now we can see it. If I really zoom in, you see there's a tiny little gap there. But this is now the theory, and it's the theory of the infinitesimal, which is as my delta becomes smaller, I am actually making a better and better approximation of what the slope actually is. Of course, as soon as I get to 0, we can't calculate it because we're dividing by 0. But if we take a tiny, tiny, tiny amount, there we are, you see we're getting an approximation that it's 0.5. And, but if I move it here, it's now saying 0.42. This is a very rough approximation. It's not a good approximation at all. Let me move the point of interest to the origin. What if I was interested in calculating what is the slope of sine at the origin? Well, if I, again, move, so I'm getting closer and closer and closer, so I'm making a better and better approximation, you can actually see that it gets to 0.99, and then we actually get to 1. Eventually, it is undefined. So that is the essence of differential calculus. We can define a slope, and even on something that's wavy, curvy, there is a way for us to define the slope. It actually is where we can look at an infinitesimal small size. We can define the slope. Not really in the scope of what I want to do. I just really, from going forward, we're going to look at mathematical functions, and I will say this function has a gradient. I think you understand now that any of these sort of curves, we can calculate what the gradient is, what the slope is. And there is, in general, a way that mathematicians build up techniques so that for any function, we can actually calculate what the slope or gradient is. Pretty much out of scope for what I want to do, because I don't really want to make this into a calculus lesson. But I think for going forward with the rest of the course, this, I hope, is just a reminder of what we mean by slope. I will be back soon, and I want to talk a little bit about more history, the work of Sir Isaac Newton. I think Isaac Newton's work is fundamental and absolutely relevant to machine learning. And then I think we'll start to get into neurons. Let's get going with some real ML. So I look forward to doing that, and I will see you soon. Bye.